All right, let's do a simple explosion case using exploCFD. I'm just going to start the software here. And we're just going to run a very simple case. Your flash screen, by the way, may be different to mine. And once you see this user interface, this first button here allows you to load files. The PDFs are really what we load. And if you go to the drawings and setups, you'll find a whole bunch of drawings. Load something like load layout 1A. And you'll see loading. Don't do anything until you see not processed. And then click on it and the drawing should appear. If you happen to click on it before, nothing will appear and you have to go through the whole process again. Okay, the first thing I'm going to do is using the right mouse button, I'm going to select a rectangle in blue here around the red rectangle. So from top left to bottom right, that's my selection. By holding down the right mouse button, everything goes red after I do that. And if I right click again somewhere, I can select exclude selected lines, and you can see everything goes purple here. And that what that is doing is basically it's telling the software that these lines that are in here are not to be treated as walls, to be completely ignored as if they are not there. Obviously, we do want them to be there. We've got a few buildings and a large blast wall. So I'm going to select a smaller rectangle within the red rectangle. Again, top left to bottom right by holding down the right mouse button and then release. Everything goes red. Right click again and go include selected lines. So now these lines will be treated as walls. You've obviously got a few buildings here and a very large V-shaped blast wall. The reason I did this is obviously firstly to show you how to select and deselect lines. There's often cases in plot plans where lines are not meant to be walls. For example, demarcations of streets or some other fictitious lines like crane turning circles, for example, that could be on the plot plan. You don't want to include those, and so you exclude them. The other thing is the PDF generally, under the boundaries of which are along this red rectangle, and underneath the red rectangle, there are lines that you could see clearly here. If these lines are not excluded, they'll be treated like walls, and that's obviously not what we want, because if they're walls, you're going to get shock waves reflected off of them. It's as if you're doing an explosion in a massive room. So we excluded everything, and then we went back and included what's on the inside. Now we need to set the dimensions of the domain, right? And in order to do that, usually on a PDF, there's usually a scale that you can apply. You just need to measure the dimensions of the drawing. Now, PDF drawings could be any size. There's no rhyme or reason. The physical size of the actual drawing. So what you do is you measure the line by, so you measure the dimensions of the drawing, and I'm going to do this again. So you select this tool here. It's called Polygon. It's actually a measuring tool, and then just a click here on the top left or any one of the vertices of the red rectangle, another click on another vertex, and a third click on the third vertex, and then just move away from the drawing and right click to get out of it. Now I've got the dimensions here to be 1.646 and 2.582. I happen to know that the scale here is 1 to 200, so I'm just gonna multiply these numbers by 200 as best as I can. So that would be 329.2. It's always width by height. So the width is that times 200, so that's 329.2. And this would be 516.4. You may have just slightly different numbers because of where you click and the relative size of the drawing. So just multiply that by 200. So you may not get my exact numbers. I'm going to just so click on use cell count, and I'm going to select just 200 by 200. That's a fairly coarse um, mesh, but we want to run things quickly, so this is it's good enough for such an open domain. Remember, we're not really concerned with resolving boundary layers and things like that. Generally, explosion modeling using CFD ignores the finer details of uh, boundary layer interactions. So by setting this to 200 by 200, you just go recalculate and then apply and close, and then we're done with the measurement part of this. And so you can hover over any of the corners until you see a blue point. Usually it's best to do the one that's far away from the red rectangle because you don't want to move the boundaries of the red rectangle. And I'm doing this point here. I'm hovering over it until I see the blue line, the blue circle. And while you're seeing that blue circle, just hit escape once on your keyboard and it should disappear. Now I'm going to zoom in by rolling the middle mouse button up. You zoom in and out by rolling the middle mouse button. And I'm going to place an analysis instance here by right-clicking and going analysis instance. And then you can either double-click this point while it's blue or right-click while it's blue and select Edit Analysis Parameters. You've got dispersion parameters. These are explosion parameters. These are high explosive uh, explosion parameters, like the one in Beirut, which was ammonium nitrate. And then we've also got Blevy parameters and dust explosions. We're going to do a gas explosion. We're going to do a propane gas explosion. So the proportion of methane, which is by default 100, is set to 0. So you double click, you put in 0, and you press enter. Make sure that you do press enter and not just click on another box. And over here, we're going to change this to 100 to make it propane. So these parameters are for C1 to C6, which is the most commonly used set of hydrocarbons in industry. And generally, the approach has been for anything heavier than C6, and it's usually a very small fraction. It's usually just added to C6. Or you can modify this last one. This last one is set as hydrogen. You can modify it to be whatever you want by changing the molecular weight, the air volume factor, which is number of moles of air for each mole of fuel, and the laminar burning velocity. And those are the key parameters for explosions. The LEL and UAL are not really relevant in this particular case. There's a couple of other parameters that we need to add. Some of these parameters could be read from the drawing automatically if this is a case, if this is, if you have a drawing that's got sufficient detail, but more accurately could be put in manually by checking things like the piping schedule. So, for example, the average pipe diameter within the gas cloud that is being ignited, let's say it's 0.1 meters. That's the average pipe diameter. And we can change fuel mass. Let's say we've got 5,000 kilograms of fuel. That's a good, healthy amount that's going to give you a good bang. The laminar burning velocity is going to be worked out automatically and is obviously going to be set as the propane one. But if you've got a mixture, it works that out as well. And now for our drawing, let me just close this for a second before or let me just scroll down. For our drawing here, our explosion is occurring on this side of the blast wall. and we want to check the effect of that explosion on the buildings behind the blast wall. Um, there is no detail here, but if we have some congestion, if we have some pipe work, we can put in this parameter, and we can put in the volume blockage ratio. These are and the confinement, which you can use. It can work out automatically from your drawing, or you can override it. So I'm going to set a confinement. So if we're looking at let's say a refinery or just a congested process area like this, you've got a lot of pipe work, a very healthy, large VBR value, volume blockage ratio, and you've got a fairly good confinement as well. So I'm going to change the confinement to say 0.5. We're going to change the volume blockage ratio to 0.15. I'm going to go through these parameters, by the way, in the lecture. So we'll get into the details, or we'll talk about some details, time permitting, of these parameters. And that's all you really need to set as far as the explosion is concerned. You need the footprint of the gas cloud, and we're going to set that in a minute. And that's all really that is required. It's quite easy to run it. So again, what we're looking for is a gas cloud, which I'm going to set now. I'm going to set the footprint of this gas cloud being ignited within a congested region with a lot of pipe work on this side of the blast wall. And the question is, does this blast wall protect these buildings from the explosion behind it? Now, you may know the answer already, but it's a surprisingly common question in industry. And it's one that you cannot solve using, multi-energy method, or the game correlation, or TNT equivalence, because all of those are one-dimensional radial methods that don't account for any obstructions, and certainly don't account for shock wave reflections and so on. So I'm gonna place the footprint of the gas cloud. Now, ideally, this gas cloud should be of the appropriate dimensions. It's usually in industry, in all CFD, it's usually taken to be a rectangle, just for ease, but you could modify the shape of the rectangle um, by um, you know holding down the Alt button and reducing the gas cloud dimensions from various sizes. So this is probably more indicative of a real gas cloud shape. Remember, we've got a fairly coarse set of cell counts on this drawing, and the higher the cell count, the more, let's say, realistic you can get a gas cloud shape to be. But in general, even if you've done a dispersion calculation and figured out the exact size, location, and composition of the gas cloud, this is usually converted into an equivalent stoichiometric gas cloud of rectangular shape. So we're running a stoichiometric gas cloud here, and this is generally the worst case scenario for these types of explosions. We're all set. All I need to do now is set the time step, the number of iterations, the right frequency, and the simulation time. So I'm going to again go with a very large time step. I'm going to delete a couple of zeros here. So we're doing, this is a millisecond time step. We're going to run about 1,500 of those, which makes it a total time of second and a half, and we're going to output every 50 iterations, and so the software will run either until you reach the product of the iterations times time step. So 1 millisecond times 1500, that's 1.5 seconds. Or this time, whichever comes first. So by leaving this at 3.5 seconds, I'm effectively going to run it for 1.5 seconds. You don't have to set this to 1.5, but if you set it to something under 1.5 seconds, it'll stop there. And that's it. All you have to do is click perform analysis, and what's going to happen is you're going to start getting calculations in exploCFD. Now it's calling the CFD engine SU2, and in a few minutes, maybe 3 or 5 minutes, depending on your processor speed, it should give you the results. I'm going to pause it for a few minutes, and then we'll look at these results. Okay, well, as you can see, the computation has finished. It took a few minutes, and the software immediately pulled up the post-processor, which is ParaView. So you could see the screen for ParaView open. And all you have to do to start visualizing the results is press apply. And you could look at some of these parameters here. If you look at pressure, for example, you could see the pressure over a period of time. Of course, we need the so-called overpressure, which is pressure above atmospheric pressure. And so there's two ways to do this. You can use one of the macros. There's a macro called overpressure. So if you can go import new macro and then go to the macros folder and then find overpressure and select OK, it will appear. And then once it appears here, you just press the button that says overpressure, and it'll calculate it for you. Of course, you can do it manually. I'm going to delete this and do it manually by right-clicking the flow and going Add Filter and go to Data Analysis and just select Calculator and just type the name. You could call it overpressure. And it's a good idea to add the units, and this is in pascals. And you just go pressure, which is a parameter that is already in there. You could select it from scalars, by the way, if you're worried about spelling and so on, minus the atmospheric pressure, which is this 101,325. And it calculates it. And then now it's displaying overpressure, and you can maximize the scale. You could change the coloring of the pressure, overpressure. You could play around with the location of everything, and you could even, if you select edit here, if that's not open, you could use a logarithmic scale here to show the overpressure more clearly. And you could see that by default for logarithmic scale go from 1 to whatever the maximum is, but you don't want to see 1 Pascal. It'll show you details that are not relevant, this dark blue stuff here. So from 100 pascals, which is still nothing, to the maximum should be fine. And what I'm going to do now is I'm going to play through the propagation of this overpressure. And what you could see, of course, is the shock wave wrapping itself around the blast wall and then impinging on the buildings. You can see reflected overpressure here, the red part here, the reflected overpressure, the pressure, the dynamic pressure is basically stagnated, and so you get maximum pressures in on walls that are directly opposite or in the opposite direction or in the perpendicular direction to the flow direction. Obviously, the pictures are much more detailed than what you would get from a simple one-dimensional calculation. Um, and if you wanted to look at some more detail, what you can do is we can take a look here and add, for example, go to data analysis and go plot over line. And you're going to get this line here that by default crosses your entire domain. But let's say you just want to see the overpressure on this middle building here. So we zoom in and just adjust the direction of this line and its location. Bring it as close as possible to the wall, but not in the gray area. So it's still in the blue. And just make sure sometimes when you play around with this line, what happens is the z coordinate becomes non-zero. Remember, we're looking at a slice of the flow on the ground. exploCFD is a two-dimensional, produces two-dimensional calculations. The software can produce three-dimensional results, but it's configured deliberately to run two-dimensional calculations. And we'll talk about why that is when we meet. So just make sure that the z coordinates for the um, beginning of the line and for the end of the line are both 0. Otherwise, you won't get any results. And just click apply. And you see a whole bunch of results. And we don't really want any of that. We just want one thing, which is the overpressure at the moment. You can see it's very low overpressure at this location. This is X coordinate along the line. So this is the beginning of the line, the end of the line. Beginning of the line is 0, end of the line is 45. And this is overpressure in pascals, which is really nothing. You're looking at just noise here at the moment because the shock wave hasn't reached it. But if I play um, or if I scroll through here step by step, you could see it's still noise. But as the shock wave approaches, you could start to see it's still very low, 60 pascals, but now it's starting to climb to 0.19 bar, and this is probably the maximum, about 0.32 bar, and then it starts to drop off again as the shock wave passes the domain. All right, let's go back and take another look. Obviously, you don't want a changing graph over time. What you want is the time history of the overpressure. And so what you can do is just right click here again, go to add filter, data analysis, and plot the data over time, and click apply. I'll always, again, it's giving you a lot of results. We only want one thing today, which is the overpressure. And you could see the typical triangular shape that occurs over the period of time that is um, that we've modeled. These are time steps, by the way. So each unit here on the x-axis, this is obviously overpressure in pascals, the y-axis, but the x-axis is each output time step. And if you remember, our time step was 1 millisecond, and we wrote every 50 of them. And so each unit here represents 50 milliseconds. And so the difference between here, which is about 13 time steps or 13 outputs, and here, which is 20. So between 30, so you got 7 time steps. 7 times 50 is 350 milliseconds. So 0.35 seconds. The duration of the explosion is 0.35 seconds approximately. And that allows you to calculate the area. If you know the base of the triangle, you know the height, you can calculate the area. And the area, of course, is the impulse that's delivered to the building. That's the energy. Delivered to the building, so you could um, quickly approximate that. That's a basic overview of some of the capabilities of exploCFD. Hopefully, in the lecture, we'll talk about the details behind the way that the software operates, and look forward to talking to you then.